One of the most important things we do in math is solve equations. Here are some examples of equations. They're just one expression set equal to another expression, and our task in solving them is to find a value of the letter that will make the statement of equality true. Well, as I say, there are different kinds of equations. We're going to start with the linear equation. Here's an equation of that type. Here's another type of equation and a third type. And all of these fall into different families that we'll be examining from time to time. Another type of equation, another category of equation is this one. This is called an identity because this equation is true for all replacements for x. All real number replacements for x will solve this equation. A lot of times equations of this type are used to illustrate properties in mathematics. This one is illustrating the distributive property. Now these other equations are called conditional equations because their solution set would be not the set of all real numbers. Okay, so we're mostly concerned with conditional equations. First type we're concerned with are linear equations. Linear equations are all the equations in the world that can be placed into this form, where a and b are real numbers. Now, the first equation we had up here is a linear equation. It was 3x minus 5 equals 7, and it is linear because it can be placed into that form. And we can place it into that form like this. We subtract 7 on both sides and then rewrite this as 3x plus a negative 12 equals 0. Then we have it in this form, the form of a linear equation. But writing equations into a certain form is not what we're mainly concerned with. We're mainly concerned with solving equations. Now with linear equations, the solving process is one of just simply isolating the letter on one side of the equation or the other. Now here's that linear equation, and if we want to isolate the x on one side, then we perform various operations that will undo the operations that we see here. We see subtract 5, and we undo that by adding 5 on both sides. Now the notion is to, in this isolation process, is to first isolate the term or terms that involve x. So here this term involves x, and we'll isolate that by adding 5 on both sides. When we add 5 on the left side, we'll get 3x. When we add 5 on the right, we'll have 7 plus 5. Now, basically, we are allowed to do a number of things. We're going to write a series of equivalent equations in order to arrive at a solution, but basically we're allowed to swap sides of an equation if we want to do that. We can add or subtract numbers on both sides of an equation. We can multiply or divide numbers on both sides of an equation and be safe in doing those kinds of things. All right, and that's really all we're doing here. Collecting on the right, we get, let's see, 12. And then we want to further isolate the x, so we'll do that by undoing the operation we see here. We see 3x, which means 3 times x, and we undo that by division. So we're going to divide on both sides by 3, and I'll show 3x over 3 equals 12 over 3. So x then is 4. The really nice thing about equations is that we can always check to see if our answer is correct. And we do that by replacing the value of x that we find and putting that value into the original equation to see if we have truth. Now, if we replace x with 4, we can do this mentally, or we can actually do it sort of algebraically or by hand. But if we do it mentally, it works like this. Replace x with 4, we would have 3 times 4, 12. 12 minus 5, 7. 7 equals 7. Yes, that's true, so this is indeed the solution to the equation. By the way, equations generally they can have one solution, they can have 2 solutions, they can have many solutions, they can have no solutions at all, and we'll be looking at equations that fall into each of those categories. Generally speaking, though, linear equations have one solution or sometimes no solutions at all. Here's one that has an x term on both sides of the equal sign and constant terms on both sides as well. And I'm just showing this because I want to get straight on the technique for solution. You've probably seen this kind of problem before. We want to put both terms that involve x on one side of the equation and the constants on the other side of the equation. Here's how we accomplish that. We can do both of those things at one time. If I choose to place all the terms involving x on the left side of the equation, I want to eliminate the 3x on the right side. So I'll think to myself, I'm subtracting 3x on both sides. When I subtract 3x on the right, it'll disappear over there, and it'll make its appearance as minus 3x on the left side. Now at the same time I want to remove the 3 from the left side, and I do that by subtracting 3 on both sides, and when I do that this 3 disappears and makes its appearance as minus 3 on the right side. So I've done both things at once here. Collecting over here I get 4x, collecting on the right I get negative 16, and then I want to divide on both sides by 4. The tendency here, when you have a simple equation like this and you want to divide on both sides by a certain number, the tendency is to just draw the line and put a 4 here, draw a line and put 4 here, rather than write another step. And pretty much you're safe in doing that as long as you're dealing with simple equations like this. However, a little bit later we're going to talk about solving inequalities, and when we get to the point of solving inequalities, if we have this kind of habit going on, then we could run into some rather serious difficulty in solving inequalities. So I suggest that you try to resist that temptation and you go ahead and write the separate step that says, all right, I'm going to divide on both sides by 4, so I'll just quickly jot this down. Doesn't take an awful lot of extra time or space. These go out and we have x equals negative 4. Once again, we could check by doing a substitution. Here's an equation involving fractions, and generally speaking, when fractions are involved in an equation, the first order of business is to clear the fractions by identifying a common denominator and multiplying through by that common denominator. Now here, the common denominator among the 5 and the 2 would be 10. So we would multiply through by 10, and we show that multiplication like this. We just show 10 times this term, and then 10 times the x over 2, and then 10 times 3. Now notice that in putting in that factor of 10, I just put it in between the minus sign and the x over 2 here. I just kind of popped it in to each term as an additional factor into each term. And I'm doing that in order to eliminate the fractions. Now that's equivalent. What I'm really doing here is I'm taking each side of the equation and I'm multiplying times 10, you see? And over here, the 10 is distributing through the binomial. So that's why I can write this, and that's why I go through this step. Okay, anyway, the 5 and the 10 is 2 here, so we have 2x, and the 2 and the 10, 5, minus 5 times x minus 5x, and then 10 times 3, 30. And then 2x minus 5x is minus 3x. Equals 30, and we want to divide on both sides by negative 3. So we'll burn a step that shows the division of both sides, or the division by negative 3 on both sides. These go out and we have x equals negative 10. Let's do a quick check. We have x is negative 10. Now, these parentheses are a little confusing. Let's take those out. I just want to quickly verify this solution, and I suggest you do this from time to time. That let's see, negative 10 over 5, gee, that's negative 2. If this is negative 10 over 2, that would be negative 5. Negative 5, that's plus 5. Okay, 5 with negative 2, that's 3. 3 equals 3. Yes, that's true. This is a valid solution. There is one rather special kind of equation involving fractions, and that's the kind where you have a single fraction on both sides of the equal sign. And that kind of equation, it's actually called a proportion. Those can be solved in a rather speedy way with cross multiplication. Now you could use the technique that we used earlier, that is identify a common denominator and multiply on both sides by it. But here, the fast way is to just cross multiply. Now, that means just multiply the numerator on one side times the denominator on the other side, and going both ways and putting the results on separate sides of the equal sign. Well, here, if I go this way first, I've got 2 times this, so it's 2 times 10x plus 3. And going in the other direction, it's 1 times 5x plus 6. Now the tendency is going to be to go ahead and multiply while you do this. That is, multiply the 2 times this and put the result of that multiplication here. That's going to get you into trouble. It's pretty easy on a problem that is this simple, but it's going to become difficult and you're going to make mistakes as the problems become more and more challenging. Now, you know, I'm going to spend a lot of time talking about technique and suggestions for how you ought to think about problems and what difficulties you ought to try to avoid, like this kind of thing right here. And I suggest that you follow those ideas, because it's not so much additional mathematical knowledge that gets us through more difficult problems. It's organization. And all of the things that I'm suggesting here fall into that kind of category. I'm suggesting that you organize your thinking and organize your work on your paper in a particular way. And it is so that you will be able to solve much more difficult problems later. All right, here we go. We're multiplying on the left 2 times 10x, 20x, and then 2 times 3, 6. And on the right, 5x plus 6. Now we want the terms involving x on one side. If I kick them to the left, I've got 20x already over here. Subtracting 5x on both sides gives me this on the left. Subtracting 6 on both sides, gee, these 6's both go out, so I have 0. 20x minus 5x is 15x equals 0. And now dividing on both sides by 15, I find 0 over 15 on the right, so x is equal to 0. Can that be true? Let's see. Back upstairs, we have 0 in place of these x's. Both of those terms go out, and we have 3 over 6 equals 1/2. This reduces to 1/2. 1/2 is equal to 1/2. We have truth and therefore a correct solution to the equation. Here's another equation involving fractions, only this one is a little more complicated than the one before. Now, our prescription for solution is to clear the fractions by identifying a common denominator and multiplying through by that common denominator. The common denominator contains every different factor that we see. We see an x factor, so that's part of the common denominator. We see x minus 3, that's part of the common denominator. We see an x. We've already mentioned an x factor before in the common denominator. We see x minus 3. Oh, that's already there as well. So our common denominator is x times x minus 3. It's this denominator that's our common denominator. Now, the toughest part of the problem is to discipline yourself to write that common denominator times every term. That is, to write the step I've already written here. Now, notice the composition of this step. It is common denominator times that fraction. Common denominator times this fraction. Common denominator times that fraction. You see, and once you've written that down, you can see the cancellation opportunities very, very easily. And it makes the whole problem very easy. But writing this step is tough to do because it's a lot to write. But if you take the time to write this step, you'll never get a problem like this wrong. All right, let's see. The x's go out here. We have x minus 3's going out here, so we have simply 3. The x's go out here. We have x minus 3 times 4. Well, that's 4 times x, 4x. 4 times minus 3 minus 12. And on the right, the x minus 3's go out, so we have 1 times x, x. Now, we'd like to have our terms involving x on one side and constants on the other side. It doesn't make any difference which side we put x's on. Oh, by the way, I should probably collect the 12 with the 3 with the negative 12 first. You really ought to have this kind of idea that, generally speaking, you ought to be simplifying expressions on both sides of the equation before you begin this isolation process. So I should collect those two. 3 with negative 12, that's negative 9. Okay, now I'd like to have the x terms on one side and the constants on the other side. It doesn't matter which side we elect to have constants versus variables on. If I elect to have the terms involving x on the right, I simply subtract 4x on both sides. So I'd have minus 9 equals x minus 4x, or minus 9 equals negative 3x. Now I divide on both sides by negative 3. I'm going to do something here that I asked you not to do because I'm running out of board space here. In the next step, I would write this and then divide by negative 3. And over here, divide by negative 3. Those go out, and I find that x is equal to 3. All right, so x equals 3 is my solution. Or perhaps I should say it is my candidate as a solution, because I don't know if it's a solution until I check. Now, if x is supposed to be 3 to solve this, let's go back and have a look. Uh-oh. I see here we have a binomial in this denominator, a factor in the denominator, and if we replace x with 3, we have 3 minus 3, 0. Uh-oh, 0 times x, 0. 0 in a denominator means we have an undefined fraction and therefore an undefined equation. And therefore, 3 is not a solution to the equation. Actually, we solved it, we found a solution, it doesn't turn out to be a valid solution, so it's called an extraneous solution to the equation. This equation actually has no real number solutions. Here's another situation that involves a lot of convolution, and I'm showing it here to illustrate the idea that we need to simplify the expression on both sides of the equation before we start to manipulate putting terms that are alike, well, terms that are alike is okay, terms that are alike on either side of the equation, variables on one side, constants on the other. Okay, so here we would do this. We want to square this binomial, so x plus 1 times x plus 1 is x squared plus 2x plus 1, and then 2 times x minus 1, 2x minus 4. On the right, multiplying x times x is x squared, and let's see, x minus 2x, that's minus 1x, or simply minus x. 1 times negative 2 is negative 2. Now let's see, this expression is in simple form. I have some collection to do over here. I've got only one term that is second degree. I'll bring it down. 2x plus 2x is 4x, and then 1 minus 4 is minus 3. And on the right I have x squared minus x minus 2. Looks like we have a different kind of equation here, but we really don't because it kind of degenerates very quickly. Let's put the terms involving x on one side. I'll leave the x squared plus 4x over here. I'm going to subtract x squared on both sides, and I'm going to add x on both sides. And then on the right I have the negative 2. I'm going to clear this negative 3 by adding 3 on both sides, giving us this. And now collecting, these x squares go out. 4x plus x is 5x. And on the right, negative 2 plus 3 is 1. And dividing on both sides by 5, I find x to be 1/5. And once again, we could go through the process of checking. Well, before we leave this section, I want to show you the way of solving these equations or checking their solution by using the graphing calculator. Now, we had a problem that looked like this a little while ago. We want to check it on the graphing calculator. Here's what we do. You take all of the elements in the equation and you put them all on one side of the equation. All the terms, just throw them on one side. Now, in this situation, I would take this fraction and throw it to the right. Now, you don't have to throw things to the right. You can throw them to either side. It doesn't matter, but I'm throwing them to the right. All right, so I subtract this fraction on both sides, and this is what happens. Now, I have 0 equals some expression over here. I don't care how complicated it is. If I have 0 equals some expression, then I just think about it like this in order to graph. I think of this as y equals that expression. And now when I look at it on the calculator, I just check out the graph, and I'm looking for the x-intercept, because the x-intercept is the place where y equals 0 on the graph. You see, so I'm really finding the x that will cause y to be 0 by looking at the graph. Let's have a look. To enter the equation for graphing, press y equals. Now we have to be a little bit cautious about this fraction. The 1/2 can be entered as 0.5 or 1 divided by 2. I'll enter it as 0.5. And now minus, and now the fraction. It's important to contain both numerator and denominator of the fraction in parentheses, because each of them is a binomial. So we open a parenthesis and enter the 10x, that's 10 variable key, plus 3, and then close parenthesis, and then divided by, open parenthesis, 5x plus 6, close parenthesis. Now the graph. Now I'm on standard settings here for this graph, and it looks really funny. I mean, it has this kind of vertical line looking thing on it right through here, and it's only because I'm not on friendly settings and the calculator is just connecting every dot, and there's a dot down here that's connected with a dot way up there. That's what this graph is all about. It's not that the graph actually goes here, it's just that the calculator is connecting those two dots. There's a point in here, there's a place where this whole graph is undefined. Actually, we can identify where that is. If I go back to y equals, look at the denominator of this fraction. There's the numerator, here's the denominator. So the x value that would cause this fraction, or excuse me, this binomial to become 0 would cause this fraction to become undefined, and therefore the whole situation would be undefined. So there is a value of x that's not valid here or not allowed for this graph. Anyway, let's go back to the graph. I want to change settings so that we have decimal values or friendly values for the decimals for identifying an x-intercept. And to do that, I go zoom, and then I want z-decimal item number 4. I'm pressing number 4, and now we just see parts of our graph. And pressing trace, I would trace over to the right and over to the left. Now, it happens that on this one, the x-intercept is right here at the origin. So the x-intercept is at x equals 0. It's a real easy one to find, but the concept is very important here, that to find the x-intercept, we cursor along the graph to the point where the y value is 0. And then once we find that point, we just read the x value.